So we are now going to see how we can simulate the spreading of this SIR model we just discussed on a network. So we'll be modeling this spreading in the form of number of iterations or number of days. So you can imagine a situation where there is this measles is spreading on a network. We'll be looking at what happens at day 1, then what happens at day 2, what happens at day 3 and so on. T0. So let's talk about day 0. T is for time. So we are talking about day 0. At day 0, let's say the network looks something like this. So you see there are 6 nodes in this network, 6 people in this network, and the blue color is for susceptible. So currently each of these people is susceptible. None of them has acquired the disease, and let's say measles. So none of these people are suffering from measles. And these are the edges across which your infection can transmit, and let's say the probability is same across all the edges. Probability of infection is P. So the pathogen for measles, it is having a contagiousness value which is P. Now let's see what will happen. Assume that, and yeah, one more thing, the value of Ti we are going to be taken to 1. So although it might not sound realistic, but in the case of measles, we can't say that you remain infected for just 1 day and after that only you just acquire lifetime immunity. You remain infected for a long period of time. But for the sake of simplicity, let's take for the time being Ti equals to 1. In the next example, we'll increase this value and see what happens. But for this example, we take the value of Ti to be 1. So here is a new kind of measles, let's say. This measles keeps you infected just for 1 day, and after this 1 day, you acquire lifetime immunity. So this is the network at day 0, and at day 0, this node 1 gets infected. So this node 1 gets measles the 0th day. What will happen on the first day now? Now this node 1 has 4 neighbors, 2 and then 3 and then 4 and then 5. So it has 4 neighbors, and it tries each of these neighbors, it tries infecting each of these neighbors with a probability of P, and let's say it's able to infect node 3 and node 5. The first day, node 1 infects node 3 and node 5. Now you might you might ask me a question here. How do I decide which are the nodes which node 1 is infecting? Sorry. How do I decide it's going to be node 3 and node 5 only? And I will tell you that this is a very random process as we discussed before. So I'm going to toss a coin for each of these edges. So if the probability of infection is 0.5, I'll toss a fair coin for this edge, for this edge, for this edge and for this edge, and I get a tail here, I got a head here, I got a tail here, and I got a head here, and I did it. And you see now, so what will happen? One simulation of this model can go like this, where node 1 has infected node 3 and node 5. But if you simulate it the second time, you again start from this graph and you again toss the coins, you might get some other result. So it's a random process. Unlike in the case where we discussed how ideas and behaviors spread on a network, everything there was deterministic. If you were given the snapshot of a network at a particular time, you would for sure with very certainty you can tell what would happen at the end. But here in this case, there is less certainty. It's more of a random process. So let's say node 1 here infected node 3 and node 5. Now see, node 1 was infected at day 0 and now it is day 1. So what's going to happen at the end of day 1? At the end of day 1, our node 1, it's going to be recovered. So node 1 is recovered towards the end of day 1, but it has infected these two nodes in the network, nodes 3 and node 5, and now on day 2, node 1 do not get to infect anybody, but nodes 3 and nodes 5, node 3 and node 5 start doing their work, and let's say node 5 end up infected node 4. So node 3 here is unable to infect any of its neighbors, and node 5 here infect node 4. Node 3 here, it's unable to infect node 2 and node 6. and node 4 as well. And you see node 3 can for sure not infect node 1 because node 1 it has recovered from the network. Overall, node 3 gets nobody it could infect, but this person, node 5 here, infects node 4. What happens next towards the end of the day 2? So these node 3 and node 5, they were suffering from day 1. They suffered at the end of day 1, right? And now they have passed 1 day of infection. So towards the end of node 2, both of these nodes will become recovered. And on day 3, it is node 4 which goes around and start infecting the people. And let's say node 4 is unable to infect anybody. Node 4 obviously cannot infect node 3, node 1 and node 5 now because they have recovered. It can infect node 6, but let's say it is unable to infect node 6, and towards the end of day 3, node 4 also gets recovered. What will happen on day 4 now? On day 4 there are these 6 people, out of which 4 have recovered, 2 are susceptible. Infection gets over. Because for this process to go on further, we need a node, we need a red node here. We need a node which is infected, but now there is no node here which is infected. No red node here. So what will happen? The process will stop. So this was one simulation we did where we took the value of Ti, that is the infection period, to be 1. Every node remains infected for 1 day. Let's now look at another example, and let's say I have changed this infection period to 2. Now you remain infected with measles for 2 days, and after these 2 days you recover from the disease, and again this is node 1 which catches the infection at day 0. So now you see node 1 will get 2 days, days 1 and day 1 and day 2 to infect its neighbor, and it will recover at the end of day 2. So node 1 here, let's say day 1 it infects node 3. Just node 3. And then comes day 2. Now at day 2, both of these nodes will be infecting people. Node 1 as well as node 3. So let's say day 2, node 3 infected node 2. Node 1 is unable to infect anybody at day 2. Or let's say rather, node 3 infected node 2 and node 1 is able to infect node 4 at day 2. So node 1 got day 1 to infect people, and it's also getting now day 2 to infect people because it remains infected for 2 days. And towards the end of the second day, node 1 recovers. Now, during the third day, all of these 3 nodes, 2, 3 and 4 get to infect their neighbors, and let's say node 3 infects node 6. If you look back at this network, so let me show you. So this node 3, it was infected at day 1, and then day 2 it infected node 2, and again at day 3 it infected node 6, and at the end of day 3 what will happen? It will recover. And now what will happen at day 4? Nodes 2, 4 and 6 get to infect people, and let's say node 2 infects node 5, and what will happen towards the end of this day? Nodes 2 and 4 will recover. You can easily guess what will happen next towards day 5. So towards day 5 also node 6 and 5 will be infected, and towards day 6 both of these will be recovered, and towards day 6 both of these will be recovered. So at the end all the nodes in this network will recover. So this is how we could have simulated it for the value Ti equals to 2. So please note that it is one possible simulation. Every time you simulate it, this network will go and it will be infected in a different way. Okay. So here what we talked about, let's quickly recap. There was a node. So the node can be either susceptible or a node can be infected, and it remains infected for Ti time, during which it infects other people, and finally the node gets recovered. Something like in the case of measles. Can I use the same model if I want to simulate the spread of a common flu? What will happen? Or let's say a common cold. So this infection might, so this model might not hold good there, right? So in common cold, yes, you become susceptible, you were susceptible, and then you become infected after coming in contact with an infected person. Then will you be permanently recovered from common cold? It never happens. What happens is, after recovering from common cold, you enjoy for some days, and or let's say some months, or let's say some years, but after that again that common cold infects you. So what happens is, instead of going to this recovered state, you go back to the susceptible state. So susceptible, infected, and after remaining infected for TI time period, you go back to the susceptible state. And this model is called the SIS model, because S refers here for susceptible, I is for infected, S is again for susceptible. So you become susceptible, you become infected, and then you again become susceptible. And this model is used for something like a common cold, which can, a disease which can infect you again and again. And I'm quite sure that you can now create a simulation of SIS model on a network on your own. But still, in the next lecture, I'll show you how can we simulate a SIS model. How can we simulate an SIS model on a network? So now we are going to look at one simulation of the SIS model. We have looked at the difference between the SIR model and SIS model. Let me quickly recap it. So in SIR model, here we were having a node, and let's say this node is susceptible, that is, it has not got the infection. And then we have seen that from susceptible, this node can go and move into an infected state. So this happens after this node comes in contact with an infected person, and this node becomes infected, and it remains infected for TI period of time, during which it keeps infecting other people. And finally, what happens? This node, it either recovers, that is, it develops a lifetime immunity against that disease, or it leaves the network. That is, let's say this node dies away, in which case we say that this node has been removed. So this was our SIR model. And our SIS model was a little bit different. It was for a disease which can infect us time and again, such as a common flu, common cold. So here again we have a node which can be initially susceptible, and then when it comes in contact with an infected person, this node, it becomes infected, and it remains infected for TI period of time. And after this period of time, what happens is, it again goes back to the susceptible state. So there is no recovered state. After some time, this node becomes susceptible again. Then it might come in contact with an infected person and again become infected, and so on. So how will this simulation of such a model look like? So this is our SIS model, and we are going to see how will the simulation of such a model look like. So let's see. So let's take a network again. So I'll take a network here. Let's say there are 5 nodes in the network. 1, and then 2, 3, 4, and 5. And I'll put some edges between these nodes. Let me put some edges. Let's say from 1 to 5, from 1 to 2, 1 to 4, 1 to 3, let's say, and then let's say from 2 to 3, 2 to 4, 3 to 4, 3 to 5, 4 to 5. That's it. So let's say these many, it's a network consisting of 5 nodes, and let's see how an epidemic or how a contagion will spread here. And here we are talking about the SIS spreading model. SIS. Initially, all of these nodes shown in this network, they are susceptible. So we were showing susceptibility by blue color. So let's make all these nodes to be susceptible. So 1 is susceptible, and 2 is susceptible, 3, 4 and 5. All these nodes are susceptible. Now this is T0, and let's say at T0 an infection comes and infects 1. So our node 1 is now infecting from common cold. And our value of Ti, that is the time period during which a node remains infected, let it be 1. So one node remains infected for 1 day. Now let's see what will happen during the second day. So we are modeling what happens during during the first day. So initially there was a 0th day. Now comes the first day. So now first day, this node 1, it will look at all of its neighbors and try to infect some of them. So let's say node 1 becomes successful in infecting this node 2 here and node 4 here. So during day 1, node 1 infected this node 2 and node 4. And by the end of day 1, what will happen? Node 1 will recover because our Ti, it is equal to 1. So towards the end of this day, node 1 will recover. After recovering, it will not go back to the recovered state. It will go back to the susceptible state as we have discussed. So it loses its common cold and come back to the susceptible state. Come back to the susceptible state. First day over. Let's now see what happens during the second day. So now is the second day. Second day, node 2 and 4 will look at their neighbors and will try infecting them, and let's say they become successful in infecting node 3. So now at day 2, on day 2, node 3 catches the infection, and again towards the end of day 2, node 2 and node 4 will go back to the susceptible state. So node 2 and node 4 now go back to the susceptible state. So this is node 2 here and node 4 here. And then what can happen during the third day? Let's say now comes the third day. So now on the third day, this node 3 is infected. So what node 3 will do? Let's say it infects node 1. Do you see what happened just now? It infects node 1. So node 1 has previously also become infected and it infected certain people. It became susceptible, but now this node 1, it again gets infected. So this node 1, it gets infected here, and towards the end of day 3, this node 3 now, it comes back to the susceptible state, and this process keeps on going. So node 1 may then infect certain nodes, and then those nodes will infect certain nodes. But suppose at this iteration what happens is node 1 is unable to infect anybody. So we are talking about day 4. So let's say at day 4, node 1 is unable to infect anybody, and what will happen towards the end of this day, towards the end of day 4? Node 1 will again go back to the susceptible state. And do you see now what has happened in this network? Everybody now comes back to the susceptible state. There is nobody who is infected. And as soon as this happens in this network, there is not even a single node which is infected. Everybody is susceptible. What will happen is the process stops. So this was the simulation of SIS model on a network.